squared. I'll do this. Okay, I'll do some side work because the rest are very repetitive. So from 250 millimeter squared. Okay, so we know this millimeter over here. Okay, this millimeter. Hold on. This millimeter over here means times 10 to power minus 3, right? So m over here means it is the unit, right? The other m is the magnitude. So this is mini, right? So we know we have unit of 1. Then you have smallest mini, micro, okay? Then you have kilo, you have mega, you have giga. All right, so this is times 10 to power minus 3 times 10 to power minus 6. This times 10 to power 3 times 10 to power 6 times 10 to power 9. Okay, so the m over here, sorry, this is in fact a capital M. Kilo is small k. Okay, kilo is not big K. Okay, don't ask me why. I just being obedient. So mini is times 10 to power minus 3. Right? Right? So from here you write down 250 times 10 to power minus 6. Why? Because 3, the exponential term is 3 multiplied by 2, you get minus 6. Okay, so this is an easy way of doing it. If you cannot remember, just follow this method. Okay. Okay, coming back to here, then you have deflection at point 3 now. So point 3 can only see the 600. The length did not change, but the cross-sectional area become 400 times 10 to the power minus 6. The material is a constant. Okay, so 600 power 3 times 0.15 divided by 400 power minus 6 divided by, oh, I don't need to divide by E. So it's 225 positive. And finally, deflection of 4, okay, is 0 because it's not seeing any load. The 600 is above section 4. Okay, so this is also 0.15 divided by 400 times 10 to the power minus 6 and divided by E. So this is equal to 0. Okay, so now we are going to add everything. Okay, so summation of the deflection due to the applied load is equal to 1 over E, 540 times by 10 to the power minus 6 plus by 360. Oh, not minus, is plus 6, sorry. 360 times 10 to the power 6 plus by 225 times 10 to the power 6. Okay, so 540, 360, 225, 1125 times 10 to the power 6 divided by Young's modulus. Okay. So now we have determined the deflection due to the applied load. Okay. Then the next thing, I'll let you guys copy. Anyone, any questions so far? Yeah, it's very repetitive for at this stage. Okay.
Sir, at the
Yes.
second deflection point, why did you use 600 rather than 300?
Because based on the hangman analysis, right, it's not seeing the 300. Okay. And Yehi, I don't think you show up for my first lecture. Am I right?
Yes, there's issues with the
It's
other
okay.
things.
It's okay.
I
Don't
want to
worry.
speak to you about it.
No. I'm not saying that you did not come. I understand you register late. Okay. So what it is I'll draw a very quick hangman. What do I mean by hangman?
Sir, I had a question about that. Does that work horizontally as well? Or is it a different system that we use?
Now everything is vertical. So there's no horizontal system, right? Hello?
Yeah, but like in our quiz question, it was horizontal.
Yeah, but if horizontal, what I tend to do is I tend to rotate to make it vertical, right? It's easy to
Oh,
visualize
okay.
it
So it
vertically.
would still be the same
Yeah.
forces.
Okay.
Okay.
Okay. So, what do I mean by the hangman theory? Okay. Now, at this point, so let's say I call this point my point D. Okay, I call this point my point D. Okay, and then I call this point my point C. Right. So at point D, so this part I call it body. This part I call it my hip. Okay. So at point D, you can feel your body and your hip. Right? But at point C, where your hip is, can it feel the body? Right? So the answer is no. Okay. It can only feel the what? At point C, you can only feel the hip. Okay. So this is why at section 2, I don't need to include the 300. I only need to include the 600. Okay. Yeah, is that okay for you?
Yes, it is. Thank you.
Okay, if not, look to last week's lecture. Okay, I think I did like a good half an hour. And then I'm seeing a chat. Yep, it's right. It's regarding the redundant load. I know this is repetitive. We've seen this before, Eugene. Why are we doing this? Okay, I understand. The fact that you have seen the first part before I could recall is good. So now you understand why the load are applied this way. Okay, now is the redundant load. Okay, so step number 2. Okay, so step number 2. Is we're going to introduce the redundant load at point B. Okay, we're going to introduce the redundant load at point B. So I'm going to take this entire diagram over here. And I'm going to paste it here. Okay. So that's our point A. We have a pin support over here. Right. So now we are going to push a redundant load at RB. Okay. RB is where we're going to. Yes.
Can I please zoom out a little bit?
Oh, I do apologize.
Yeah, that's good. Thanks.
Okay. Can you still see or no? Enough or no?
That's good. I just wanted to see what was above the.
Okay. So that is the redundant at point B. Okay. You got it. So now, as I said, we do not consider the 300 kilonewton and the 600 kilonewton. The 300 Newton and the 600 kilonewton, which we already considered in the first part. Okay, which is remove the support at B. Now we're going to introduce the redundant load at B. So you don't need to consider the applied load. Okay. Now we're going to divide this into 2 sections. Why only 2 sections? Because AC, okay, and CB, the length are the same, but the area of AC is 250 millimeters squared, and the area of CB is equal to 400 millimeters squared. Both of them CRB. I repeat again, both of them CRD. I'm sorry, not C. Okay, structure got no eyes. Both section of AC and CB feel the force RB. Do you all agree or disagree?
Agree.
Agree. You can disagree. I'm not a communist, okay? I mean, I'm from Singapore. It's a republic, but we are run by communists, okay? Now, let me elaborate why AC and CB can feel RB, okay? Now, let's say we are in the hangman situation. If I push the load, so this is our RB, right? If I push from below at your feet, okay, if our joints are, I mean, your joints are not as sensitive as mine because I'm older than you, okay, I could feel it. When I push RB, my hip, my elbow, right, is able to feel the relief in stresses, right? Now, what if now I push or we push from the hip? If we push, I call this our RC. If I push from RC, what will happen? Only the body feel the assistance, right? But the anchor over here did not sense any relief at all. Agree or disagree? Yeah. So I want you to like embrace this hangman thing. Okay. I hope you guys do. Right. Coming back to here. Right. So we are going to calculate the redundant load of 1 and redundant load of 2. So the formula is still the same. Okay. So now deflection due to the redundant load at section 1. So it's equal to, yes.
So will AC and CB feeling the redundant load be dependent on the load at the top, like at A, or would that always be the case?
So A, did I draw anything at point A? No, right? So everything is dependent on RB.
Right, but it's hanging off of the pin at A, right? Like the
Yeah,
whole.
A is hanging, but there's no applied load at A, right? A is our fixed point.
Right.
Okay, you cannot just put a load down there. Okay, the way of solving this is keep A over there. Do not consider the load at A. A is your reference point, so everything is 0. Okay, analyze everything from below onwards.
Okay, I guess I'm just trying to understand if the redundant load would always affect the entire structure.
What is your question again?
I'm trying to understand if the redundant load applied at the bottom would always affect the entire structure.
It will affect the entire structure, but not at point A. Point A has no distance.
No, not at point A, at point B, like where it is right now. Like for every say for a different type of application, like would the redundant load like at the bottom of the structure always affect the entire structure?
If it's compression, yes.
Okay.
If it's tensile, you have to be really, really careful. And it's dependent on where the load is applied. Okpara, do not take the example of one problem strand to look at another.
Okay.
Okay. Understand the fundamental mechanics first. Okay. A lot of time it's not your fault. When I was young, I was the same. I will look at the solution procedure of one example and try to mimic the same on the other, and it's not always possible. Sometimes it works, don't get me wrong, okay, but not always. Okay.
Okay.
I'm not
Yeah,
saying
I'm
that.
just trying to see if there's a specific pattern to it.
Yeah. So the thing you have to remember that applies to everything is this. Okay. This applies to anything, and this rule applies for everything. You understand? Okay.
Yeah.
So once you have these two mechanics foundation, okay, you can apply to any problem. You get what I mean? But do not like like say, okay, if this problem is like this, on the next problem is going to be the same. It's a very risky commitment.
Right.
Okay. So from here, reflection of B, I think